Okay, thanks Arthur, and welcome everyone. This is the second in a series of 3 talks. Welcome everybody again. My name's Allan Blair. I'm a principal consultant in mining with SRK in the UK. This is the second in a series of seminars a series of 3 seminars that we'll be delivering today. Aimed at describing how to deliver strategic value in the planning process. And that planning process can be for an operating mine or in feasibility study assessment, so at various stages. My topic today is in relation to mining, dilution and loss. And it's an area that I think is underestimated in terms of its potential impact on operations. And I'll provide a couple of case studies later that can show when something goes wrong with dilution and loss estimation and reconciliation for a mine site, it can go very wrong indeed. And I'll try to demonstrate to you and help and assist in understanding the importance of this particular area of technical investigation. So moving on, we'll look at the key issues in relation to dilution and loss estimation. Then we'll have a look at some of the definitions for those that are unfamiliar with the terms, and even for those that are familiar with the terms dilution, loss, mining recovery and reconciliation. The definitions vary quite considerably. And so it's important to understand, for comparison purposes, what definition you're dealing with. We'll then look at some of the sources of mining dilution and loss, both in a planning and operational sense. We will then look at some of the methods of estimation. So we'll focus in particular on some of the modern techniques and in comparison to global factors that are still quite widely used in the industry. We'll look at techniques of model regularisation, wireframe modelling, grid modelling and the like. So we'll look at the modelling approach and then we'll do a quick comparison with industry benchmarks for dilution and loss for both open pits and underground mining methods. And then look at some of the historical performance statistics, which I'm sorry to say aren't that good. Finally, I'll go through a couple of case studies that can help demonstrate when things go wrong, they can really go wrong, and then recap on the areas that I've covered. And in the end, hopefully take a few questions. Okay, so apologies in advance for the Russian translation. I have some Russian translation in the presentation, but I'm told it's very poor, so apologies in advance for that. So this sort of covers the areas that I'll be looking at and what I mean by sorting the chaff from the wheat. Some of the misconceptions and problems in calculation and some of the lies that occur in terms of the way people go about estimating. So I guess one of the premises I have in presenting this presentation is that people often assume nominal estimates for dilution and loss, and certainly at a feasibility level there's an onus on technical people, on company staff to present a project in the best possible light. And one of the ways of achieving that is to minimise any of the deleterious aspects for a project. So you tend to find in the literature that dilution loss estimates are low, typically of the order of 10%, dilution, 5% loss. But what I would point out is that in practice, these dilution levels and loss levels can be significantly higher. And it's usually at an operational stage when you find out these uncomfortable truths. So in the process of analysing this issue, we'll look at some of the industry benchmarks. We'll look at methods of analysing halo and mixing zones in relation to dilution. We'll look at the techniques, in particular block regularisation, which is a widespread technique used both as a prelude to the open pit analysis that my colleague Fraser has outlined earlier, and used quite widely to dilute models so that they can be analysed from a detailed optimisation and design perspective. I'll also look at other techniques in terms of wireframe modelling techniques, which is a slightly different approach to regularisation, but we often use for seam-type deposits in combination with grid models. For very large deposits, these are much more time effective in our analysis. The importance of mining accuracy, we'll assess that in terms of what sort of impact that might have, and often an underestimated impact on overall levels of loss and dilution. And a range of other areas that we'll look at, identifying the areas where we have internal and external dilution, otherwise known as planned and unplanned or operational dilution and loss. And we'll look at how this whole subject interfaces with the reconciliation process for the mine. And by that I mean starting from a resource, usually what metal you have in the resource, as opposed to what metal you deliver out of the mill. And it's where the impact on the reconciliation that is most significant. So in those terms, we'll look at a couple of case studies in conclusion that will hopefully demonstrate some of the techniques and issues that we'll discuss. So what do you hope to learn? Some of the modern techniques for better estimation of mining dilution and loss. How it's practically applied. Now there'll be a number of techniques that I'll go over, so it may be high level in some areas. Some of the pitfalls to avoid. So what not to do and what to do, I guess. How that fits in with the reconciliation process. And what the downstream impact is on physicals and costs. So why is all this useful? So I think a better understanding of all these issues can help us in terms of understanding the mine reconciliation process, in the preparation of mine plans, and ultimately in improving project returns. So it's important to both collect this information, analyse it, but it's also important to apply it. So having an understanding can help us make better sense of what mining methods and techniques to apply. So say for instance you have high dilution levels in a seam deposit like a phosphate deposit. You may wish to reduce the level of dilution, and that has been demonstrated in deposits like phosphate, shale oil, iron ore, to name a few, and in bauxite most recently by application of continuous miners. So dilution levels for those sort of seam deposits can be reduced from the order of say 0.3 of a metre down to about 7.5 centimetres with appropriate application of the right techniques. From an underground perspective, once you have a handle on what your true levels of losses and dilution are, you can then make some decisions about the mining method. For instance, some of the Kazakh operations here in sedimentary style locations with relatively moderately dipping ore bodies have some issues with failure on the hanging wall, slabbing and layering on the hanging wall. And in those sort of circumstances, it may be in their best interest to adopt a backfill mining method, perhaps in the style of what's called an evoker style backfill operation or a cemented rockfill operation. So understanding what's happening at an operational level and also at the planning level can help you make decisions about the mining method and the techniques. In terms of production rates, there's well-established data that indicates that grades fall as production rates rise, irrespective of what the cut-off grade inventories are at each particular cut-off grade level. So in other words, as you stress an operation, particularly an underground operation, you tend to find that grades fall. And it's usually a function of lower grade material being included in the production stream, irrespective of the fact that it may be falling below your cut-off grade, your economic cut-off grade. So understanding that sort of relationship can help make you decisions about what sort of production rates to choose. And I guess we'll look at some of the mitigation measures, purely in terms of mining techniques. So moving on, I guess this summarises what I regard as some of the key issues that face you. For instance, if the mine is not performing, less tonnes, less grade, less metal, and that's very common. I'll present some data later that will show that in around about 38% of cases of studies during the 1980s of operations, say for instance in Australia, operations did not live up to their planned targeted grades. And an even higher level of US studies indicates that similarly they did not achieve their targeted grades. So it's quite important. So I stress the importance of accurately assessing the dilution and loss, and most importantly, what impact that has on the downstream technical and economic viability for a project. So you start off with understanding what the issues are. If you don't understand it, you can't hope to fix it. If you don't measure it, then you can't hope to fix that either. If you don't measure it, if you don't reconcile it, you don't understand it, and there's no hope of making the necessary changes to make improvements. So, one of the issues I think that faces the industry is that there's a lack of clarity in the definitions at the outset. Depending upon which country, which type of mining you're doing, the definitions for dilution and loss will often vary. So I'll provide a couple of examples here. Simply, dilution can be expressed as a ratio of waste to ore, or it can be expressed in terms of waste to a ratio to ore plus waste. And you come up with different values. For some operations, it's a convenient way of actually lowering their estimated levels of dilution. In terms of definitions, the mining recovery is generally a mirror of the loss, as I've demonstrated here. Generally, it's a function of a ratio of tonnages, recovered tonnages to diluted tonnages. Now that becomes problematic when you're looking at grade. If you're looking at dilution, traditionally, historically has been considered dilution is devoid of grade. In practice, it's rarely devoid of grade. And combined with an uncertainty in the position of your ore body, dilution levels can be quite, dilution grades can be quite significant. In some underground operations that lack visual control, dilution grades can be of the order of 50% of the in situ grade of the deposit, which can have a significant impact on estimated levels of dilution and loss. So when we talk about recovery, we're looking at expressing recovery also in terms of metal recovery, which is probably a more valid approach because it takes into account that variation in grade. Often in, I'll go through later, but in the degree of mixing of dilution with the deposit. And I'll explain in more detail, if it's non-uniform mixing of your dilution, you can have some odd outcomes in terms of the recovery, in terms of both tonnes and grade. So as an example, this is some other examples of defining dilution that I covered previously, either as a function, again, of waste to ore or as a function of waste to ore plus waste. And I'll provide a couple of examples shortly that demonstrates the different outcomes that could be achieved. So, can everybody see that okay? Or is it difficult to make out? I'll talk to it. Essentially what we have here is a demonstration of different methods of calculating mining dilution and recovery. In the first instance, you've got 10 tonne of material that's grading 3 grams per tonne. You're adding 1 tonne of dilution at 0 grade. That gives you recovered diluted tonnage of 11 grams at 2.72. And of that, there's a certain amount that's recovered. But essentially, this is the simplest case of dilution. And the takeaways are that the estimation of your dilution levels, when calculated by the different methods, is either 10% or 9%. And the recovery levels, whether they're calculated here by tonnage, a ratio of tonnage, or as a ratio of metal recovered, are the same. In the second example here, you include a diluent grade, again diluting it with 1 tonne of material, and what you find here is that the recoveries calculated are the same. And the reason for that is there is a uniform mixing of the dilution and your mineralisation, so it becomes homogeneous. So you won't see any variance in the recoveries. You still see the variance in the different methods of calculating the dilution, but you don't see the variance in the recoveries. In the third example, you're getting non-homogeneous mixing of material and possibly a positive grade performance. And in this case, you're getting a higher grade recovered because the dilution often sits on the surrounds of an ore body, so it's rarely totally uniformly mixed within the mineralisation itself. So that's reason in part you have these variances in recovery. So metal recovery in this case is where we're getting some positive reconciliation, so slightly higher grades than one would predict from the diluted resource, you're getting positive reconciliation, 95.7% as opposed to 95%. The reverse can occur with this example here, where you're getting underreporting. Again, negative grade, what I would term negative grade reconciliation, again in a circumstance of homogeneous mixing and or recovery. So in those sort of circumstances you can end up with much lower levels of recovery, estimated levels of recovery. So I guess what this example points out is it's important to understand the nature of what you're measuring and how you're measuring it. What you think are odd results, what people can say, well, it's not the process plant, it's the mining. It's not mining, it's the resource model. Often they can be simply understood by better understanding this whole process. Now, in terms of the dilution and loss estimates themselves, you may find that with dilution grades that are lower, obscures the fact that the true levels of dilution and loss are significantly higher than estimated. And this is a simple example that demonstrates that. So the same example B that we looked at before, we have a dilution grade of 0.3 and we have uniform homogeneous mixing, and we get an outcome that says we've recovered 10.5 tonne at 2.7 grams, 2.75 grams. This example here achieves the same outcome, 10.5 tonnes at 2.75 grams. So if you actually measured it, the level of dilution and loss, you will find that this same outcome can be achieved by perhaps 20% dilution at half the in situ grade of 3 grams, so double the dilution, but at a much higher grade, with which much lower recoveries. So I guess what this is pointing out is that you can achieve the same outcome and significantly underestimate the level of dilution, significantly underestimate the level of dilutant grade, and also the level of recovery. So it's very important to understand and measure what these values are, because you can achieve the same outcome with entirely different levels of dilution and loss. So moving on here, we are looking to understand the sources of that dilution and loss. And mining engineers generally look at what's called internal dilution or external dilution. And again, there are a number of names for this. Internal dilution we call plant, and it's generally incurred in the planning process. So where we have an understanding of the cut-off grade of an ore body, we'll produce an envelope or outline. This outline itself can be produced with packages such as mineable resource optimisation, or MRO, or mineable shape optimisation, or MSO, software that can be used to generate these outlines. And within these outlines, we'll often have material that is below the economic cut-off grade. So that's at the planned stage. At the unplanned stage, which is also called external dilution or operational dilution, it's often a function of the mining process. So the degree of the dilution can be dependent upon the configuration of the ore body itself, the geology of the deposit, how continuous it is it a consistent layer, is it a glob of material, the type of mining method applied. So, for instance, a strip mining operation is significantly different to conventional open pit style operation. Different underground mining methods can be applied for flat-lying deposits, which may require a room and pillar, or vertical ore bodies might require an uphole benching or sub-level stoping operation. So internal dilution is that sort of dilution that's included in the mine design. So we have a plan, shape or outline. So sources of that include the dilution that's incorporated in the resource estimate itself. So it can also include, in the cases of particularly seam deposits, any interstitial layers of waste material or intercalated or waste material. It can also be a function of the mining method itself. So in an open pit situation, it can be the real angle of the material. When you have blasted material and you've got a vertical ore body and the excavator is standing on the bench, material will roll down from that bench the angle of repose, and you can get a degree of dilution simply from that process. The internal dilution can also be a function of the requirement to mine small high-grade zones where it's only possible to mine in a certain size using the equipment that you have at hand. So external dilution is added during the mining process itself. So you need to incorporate estimates. So initially a mining engineer will plan what they're going to mine. It'll be marked up in the pit. It'll be drilled and blasted. In modern mines, they'll actually use blast movement monitoring, which itself is a source of external dilution and loss. Many operations throughout the world are using blast movement monitoring to identify where the material moves. So blasts, certainly in an open pit, are generally aligned along strike because the blast movement then is limited to reducing dilution. If you have blasts that are cross strike, you'll have higher levels of dilution. So there's many operations throughout the world that have been, in recent years, introducing blast movement monitoring to significantly reduce levels of dilution and improve recoveries. So of the order of 10 to 20% improvements, which can have a significant impact on the bottom line. So other sources of dilution and loss: poor drilling accuracy. So that's from both an open pit but also from an underground perspective. Far more important that drilling accuracy, certainly underground, and that's a function of the hole length, the type of equipment, the size of the headings, the diameter of the drilling, and that can have a significant impact. Other sources that can occur, certainly in an underground environment, will be in terms of slabbing or falling off the hanging wall or the backs of the ore body. And similarly in an open pit, we were talking earlier about real angles during the mining process that will introduce dilution and or loss. Over and under mining of the ore body, excuse me, can be an issue. Drill and blast overbreak and or underbreak. Overbreak will introduce dilution. Underbreak will introduce ore loss. And an underrated but very important source is the ability to rely on visual control in the open pit. In narrow vein gold mining open pit operations, it's very common to use an ore spotter to assist excavator operators in the mining of ore shocks and controlling how the ore is exposed, generally from hanging wall through to footwall, so as to reduce the level of dilution and loss. The importance of operator skills should also not be underestimated. And as part of that, the mining of ore patterns on day shift only. Sometimes this is not possible, but there is a preference to mine where there's good visual control during daylight hours, and that can often improve the level of dilution and loss. Haulage misallocation is another area that can be significant. In most operations, of the order of 0.5% of ore can be misdirected. And very often, operations will ignore this issue. Well-run, selected mining operations will generally employ colour-coded systems to indicate what material the trucks are carrying, and there will be dispatch control of tracking of trucks and or GPS tracking of trucks to ensure that hard-won ore is not redirected to waste. So, the methods of estimation. So previously, historically, there have been a case of using global modifying factors. And if you look at the reports that are issued in relation to feasibility studies and projects throughout the world, NI 43101 reports, JORC reports, you tend to find a high incidence of projects that have 10% dilution, 5% loss, or within 5% of those estimates. And that's quite common. And in the past, where techniques didn't exist as they do today, computerised techniques that can reduce the time frame, it was quite valid and acceptable practice to use global modifying techniques to obtain reserve estimates. Now that we have fast computer-aided techniques, we're able to do away with these global modifying factors and apply them at a more local level. So the important thing to understand is that applying at a local level is very important because the economics of a project, the net present value, which is time-based, is a function of what happens at a local level. So if a geologist comes to you and says that globally this estimate has so many tonnes at a certain grade of measured indicated material, that's fine. Globally that estimate is correct, but what a mining engineer is interested in is what happens at a local level. So are the dilution levels in the upper part of an ore body the same as in the lower part of the ore body? If they're not, they will have a more significant impact in the early life of a project. And what's important from an economic perspective is what happens in the early life of a project. So getting things right at a local level becomes far more important. But we have the computer techniques that allow us to assist in achieving this objective. So the other two key techniques that we'll describe in this paper are block model regularisation techniques, which tends to be very good in use providing dilution and loss estimates at a local level within a resource model. But in my experience, if not careful, they can be over-smoothed. They can over-smooth an ore body. And what I mean by that is introduce much higher levels of dilution and loss than they should be achieved in practice. One of the aspects of block model regularisation is the relationship with the size of the equipment and the bench height. And there is a relationship, but it also is a function of the type of mining method. So most mining in an open pit with a steeply or moderately dipping ore body should be mined from a hanging wall to a footwall. And exposing an ore body in this fashion often means that you can use a much larger bucket to mine a narrower ore body. It's just the technique applied to mining it. But in general terms, the size of the block that you're mining allows you to take a sub-blocked model and regularise that model to a larger size, and so therefore dilute the ore body. And that size is then consistent generally with the bench height that you're using and the size of equipment you're using. The other technique that we'll look at is wireframing, using to find a dilution zone. So similar to regularisation techniques, they're good at acting locally, but need to be combined with block model interrogation to give you the sorts of results that you require. So block regularisation and the selective mining unit. The selective mining unit is essentially the smallest size block that can be effectively mined by the equipment that you're applying to an open pit. So it's routinely used for estimation purposes. And what it does is it takes a finer resolution block model and dilutes this at the edges and internally. At the same time, applying a cut-off grade, economic cut-off grade, effectively applies a degree of loss. So regularisation can achieve both dilution or planned dilution and loss. Introduce that into the model that can subsequently be used for optimisation, design and scheduling. It's essentially a smoothing process, but it is tied to bench height and SMU size. This is a common feature of software modelling packages. And the regular block size is generally increased with the size of the mining equipment and the bench height. So this sort of describes the overall process. The key objective is to introduce mining and dilution on a local basis rather than globally. And it takes account of the geometry of the mineralisation. For instance, in this case, the ore body strikes across at roughly 45 degrees. Where you have a model in these circumstances, it can often be helpful to reorient it or rotate your block model so you don't have this sawtoothing effect at the edges. I've got a graphic for that shortly. So you tend to match the block dimensions, the appropriate equipment sizes, and we'll look at some techniques that we apply for selection purposes. The other important aspect is it's not just for open pit. We often use this for underground as well. So it can be used in an underground environment to effectively estimate levels of dilution and loss, though generally at larger stope dimensions. So this sort of demonstrates the overall process. You've got a sub-block model here. So you can see it's reasonably well tightly defined at the edges. In this case, it's been regularised. So you have these lower grade blocks coloured blue, blue and green, that demonstrate the level of dilution at the ore to waste boundaries. So in this case, we've taken a sub-block model and we've reblocked it to a 6 by 6 metre dimension. So you can see that it's basically added a dilution, what I call a dilution halo to the ore body. What I was talking about earlier, the orientation of the ore body, if it's close to around 45 degrees, instead of what I would call orthogonal across the page, then you might consider rotating your model. Otherwise, you tend to have this sawtooth effect on the edge. When regularisation is undertaken, very often, though not always, you can orient your X and Y dimensions are the same, and the Z dimension is variable. Often in the case of underground regularisation, you'll have the dimension orientated longer on the strike of the ore body. Usually for most software packages, the SMU dimensions are an integer factor of the resource model dimensions. So over here we've got a demonstration of, given the parent resource block size, what sort of SMU options we can have. So basically it's a case of taking the parent block size and aggregating that block size to give you a different regularisation SMU. So as I mentioned earlier, the SMU, or selective mining unit, is the smallest block dimension that can be selectively mined with a defined loader. So when we look at, for instance, a graphical representation of this, we're looking at the size of the SMU that can be mined by a particular size of equipment. So the choice of the size of the SMU will depend upon what levels of dilution and loss that you want. The larger equipment, of course, you'll have higher levels of dilution and loss. So generally, larger equipment is applied for bulk style, larger deposits. So with the regularisation approach will take into account the degree of selectivity that you require. Generally, the larger bulk deposits are themselves require a higher production level, and again that will relate to the size of equipment that you'll want to employ. And there is also an impact of the SMU on the DCF, because regularisation at a larger level and introducing higher levels of dilution and loss will be at a higher cost, downstream cost, particularly through a process plant. So when we undertake these sorts of calculations, we look at the ability of equipment to operate on certain bench heights. So different equipment sizes demonstrated in these tables here are more suited to certain bench heights and SMU sizes. So when we do the regularisation process, we take into account and have some knowledge at least what sort of equipment we're going to be running. And these sort of range diagrams provide a guide for that purpose. The overall impact of this whole process is quite straightforward, and this sort of demonstrates that process. What you see here is a couple of graphs. The one on the left, a grade tonnage curve. So the original grade tonnage curve is in black. This is the original resource model, finer resolution, smaller block size model. Once aggregated, you see an increase in the tonnage at the lower cut-off grades and a decrease in the tonnage at the higher cut-off grades. In the graph on the right-hand side, it demonstrates this by a binning technique, tonnage and grade bin. So the curve, the bar chart shifts from grey through to green, effectively pushing the tonnage towards the lower grade side. So the impact of a particular regularisation can be estimated quite regularly, and the overall impact on dilution you can estimate for different SMU sizes. And generally we do that as a matter of routine. We'll estimate what the level of dilution is, say, for a 6x6 block size, and what the level of loss is, and we'll estimate, say, what the level of dilution loss is for a block size that might be, say, 12x12. And we'll look at the equipment size, the bench height, and the impact on the dilution and loss estimates to make a reasoned assessment of what sort of regularisation we're going to apply, because that will be carried forward to the optimisation, design and scheduling stages. Now moving on now to an alternate technique, which is wireframe modelling. This in turn has its own nomenclature, definitions. So when this style of approach is often used for seam modelling, seam deposits, flat-lying deposits, but can be applied more generally, but generally has more prevalence in this area. Again, there are three main approaches. So we look at what's called an inclusive approach. And here you see it's including all of the dilution, and it assumes we recover all of the ore body. So the ore body lies within these black outlines. What is actually mined lies within these red outlines. So this is saying we're taking all of the mineralisation, plus we're incurring 100% of the dilution. The second option is what's termed the standard option, and generally it assumes a proportion of the dilution and a proportion of loss of the mineralisation is incurred. This is generally what occurs in practice, and we tend at the outset to assume something of the order 50% loss of the dilution incurred. So equal proportions of loss and equal proportions of dilution. Now, in some circumstances, you might want to adopt this exclusive approach. Now, that can be in circumstances perhaps where you have an impurity or penalty element that you want to exclude from downstream processing, and you need to maintain a very low to minimal level of dilution. So generally, in practice, we find the standard approach is what occurs in practice. So when we do modelling using these techniques, in the past, it's been difficult because, partly because of issues with manipulating large wireframe surfaces, expanding and contracting wireframe surfaces, and some of the technical difficulties involved in that. More recently, software such as Leapfrog and other software has simplified this approach. And we certainly find in the use of gridded models for seam deposits, it's helped to simplify this process further. What I'm demonstrating in this graphic here is another technique related to what we were talking about earlier about uniform mixing of dilution. So what this technique involves is recognising there's a mixing zone. So if you're mining an ore body, generally the area that's disturbed is on the contact between ore and waste. So over this surface, we can actually model the level of dilution using a mixing zone approach. Now, in my experience, it's rarely applied. It's a lot more time intensive, and in practice, it's not widely spread use in the industry. But I think in terms of accuracy of defining dilution and loss, it's a much better approach. Again, it's a case of waiting for techniques and the speed of techniques to catch up with the approach. So we were talking about industry benchmarks earlier, and in my experience, these are the sorts of benchmarks that we see in practice. So it's amazing how often you'll see 10% dilution, 95% recovery. I'd suggest that in practice that most operations aren't even close to that. Again, these sort of benchmark estimates for mining dilution recovery for underground. But the actual levels of dilution, particularly for some of the underground ore bodies, can be significantly higher. We were talking earlier about performance, and some of the statistics are actually quite damning. So, you know, 2/3 of 35 Australian gold mines in the 80s didn't even achieve their planned head grades. North American projects, only 10% achieved their commercial aims. And with almost 40% failing within a year. So they're quite damning statistics. So getting a handle on that can help you resolve those sorts of issues. So when things can go wrong, sometimes they can go wrong really badly, and sometimes it's difficult to establish the cause of the issue. This particular gold mine, it's a hard rock gold mine that we've done some work on. I won't mention names or who the operation is and the some of the data has actually been adjusted. But this serves to demonstrate some of the issues. So we've got a feasibility study that originally demonstrated there was 4 million tonnes at 2.2 grams. What they milled was 2.5 million tonnes at 1 gram. In fact, less than 1 gram. So you've got 42% of the gold recovered. When we actually went and analysed this, we found that most of the gold was actually removed at a grade control definition stage. Something like 44% of the gold. Mining, dilution and loss added a further 14%. So I guess what this serves to demonstrate is two things from my perspective. You've got to understand your dilution and loss estimates, and sometimes the only way of getting an accurate gauge on that is to also undertake an overall reconciliation to identify where there are other problems in the system. So, for instance, an additional 4% loss at mill and a significant loss between your original resource model and your grade control. This sort of demonstrates some of the issues in relation to the ore body itself. You'll see there's some problems in establishing continuity. Fraser and I actually worked on this project. I think this was one of the first things we had a look at when we took on the project. One way of getting a handle on an ore body and assessing it from a mining perspective is to take a look at the sections and plans and get a visual feel for the operation. And certainly the initial thoughts were subsequently confirmed as the project proceeded. When we had a look at this particular project, we looked to review the resource model, but also to revise the way that we looked at it from a mining perspective. So traditionally, with open pit optimisation, we'll optimise based upon the value of each block. In this particular case, we used an algorithm called mineable resource optimisation, which groups blocks as part of a group within an envelope based upon cut-off grade. So in this case, it assumes a minimum size for your block, a minimum size that's mineable. Then it takes that template and applies itself onto a block model to see what blocks grouped together exceed your cut-off grade. So in this case, we've got some included waste. So this process of using the technique called MRO can be used to flag the ore body as ore, even if they're internal waste material. We then do an assessment of what level of operational loss and dilution is incurred, and using the flag model and our operational dilution, we then undertake our optimisation, design and scheduling. So slightly different to conventional gold optimisation design. And in so doing, we demonstrated much higher levels of dilution and loss than had previously been demonstrated. And part of the reason for that is the lack of continuity at the sort of cut-off grades we were looking at. This is an African gold case study B, is an African gold operation. Again, some of the data has been adjusted to protect. What I'd like to demonstrate here is the levels of reconciliation can be very high indeed. In this case, we were presented with data that on the face of it said there was 83% return of the metal. When we actually looked at the data and did a proper reconciliation, we found that actually they were down 39%. Now, this particular ore body was high grade, so it wasn't a project killer. But for a low grade project, a 39% loss of metal will just kill the project. One of the issues we found here was they disguised the reporting by including moisture content of 20%, which is high in its own right. Most mines are lucky to have 5% moisture, and generally more in the range of 2% moisture. But what they had been doing is they'd effectively disguised the problem, presented only a 17% loss when in fact the loss was around 39%. So again, this demonstrates the importance of the assessment. When we had a look at the potential levels of loss and dilution, this, if you look in the red areas are the actual ore zones, the blue and the green are, well, the green is lower grade, the blue is waste. These patterns are very large, 50 to 100 metre patterns of ore. In these circumstances, you can apply some fairly simple techniques to determine the level of operational dilution and loss. And generally what I do is look at the grade control ore body outlines, section them, and simply ratio the perimeter of the section to the area. And then applying a thickness of dilution, you can fairly readily estimate the levels of dilution. In this particular case, on most flitches, a simple analysis like this indicates that the level of dilution and loss is probably only of the order of 2%. What we're achieving in practice was 14%. So again, it's an area of investigation. Go back to the operation and say, what's the reason for such a high level? So, in summary, and I'll quickly do this because I think we're running a little bit behind schedule. What we've looked at are some of the techniques for estimation of mining dilution and loss. So those being global factors, block regularisation, wireframe halo modelling, and we touched on it but didn't describe in detail techniques related to mineable resource optimisation, mineable shape optimisation. The MRO and MSO techniques are becoming more mainstream, and many operations from both an open pit and underground perspective are applying these techniques. And they've become much more rapid than they have been, than has been possible in the past. There's also a prevalence of grid modelling that we use that can significantly shorten the time for evaluation and analysis of large seam-style deposits. So despite, in terms of practical application, these techniques are available, in some areas not used, but becoming more widely used. But there's simple techniques that are also available. And one I described earlier, simply by sectioning your ore body and either ratioing your perimeter to area ratio or ratioing your surface to volume ratio. Then simple application of a dilution thickness can give you a very quick appreciation of what dilution and loss is like at a local and a global level. Some of the pitfalls to avoid, there's significant differences in definitions, so be careful when you're comparing between different operations. Benchmarks themselves are no substitute for proper analysis. So do the numbers. And when that's done, make realistic estimates of all sources of dilution and loss. So for instance, people won't account for truck misallocation, ore being sent to waste, and waste being sent to ore. So as mining proceeds, we should be in the habit of reconciling as we proceed, not once you've got a problem. Because as I've demonstrated with some of those case studies, the problems can be significant. 30, 40% loss. And that's usually an operation killer. So, which leads on to the last point here in terms of the project costs and returns. If you don't make realistic estimates at the outset, if you fail to monitor as the operation ramps up and as mining proceeds in the long term, then you're not going to be able to control the outcomes for the project. Having a handle on it will allow you to control the outcomes and take preventative action as you require. So I guess the key takeaway from my perspective is it's important to have an accurate and realistic estimate of mining dilution and loss, not only at the feasibility stage, but throughout the mining life cycle. Thanks very much. Any questions?
Большое спасибо за доклад. У меня следующий вопрос. И каркасная, и блочная модель, они дают границы геологических контактов в целике. Учитываете ли вы при расчете разубоживания такой важный фактор, как взрыв? Это и сеть коммутации, и характеристики взрывчатки, что в принципе непосредственно влияет на само разубоживание? Или вы просто считаете по длине контакта в целике до взрыва?
So the question was, so you
Hi.
look at the ore body in situ, right?
Yeah.
And the question is, are you taking into account blast energy?
Sorry. Are you taking into account blast and performance? Because what you showed here, I'm just trying to interpret the question. What is showed here is very good from in-ground position or versus waste contact. But the question was, are you taking into account the blast and performance in your loss and dilution estimation?
I think you can. One of the techniques we've used recently and is used quite often is the mineable shape optimization algorithm that is used in packages such as DataMine, Deswick, I think are the main ones. They generally allow you to say, this is my stope shape. It's a certain dip. This is my minimum thickness. It might be, say, you've got headings that are 4 by 4 metre or 3 by 3.5 metres. So you limit your width to maybe 3.5 metres or 4 metres. And combined with the dip and the level interval, you've got your shape. And you use that shape, which is superimposed on the block model, together with a cut-off grade to determine the shape outline. But this process can also use parameters for minimum pillar dimensions, and it can use parameters for sloughing or failure, slabbing of the hanging wall and footwall. So you can model it at that stage. Your question relates more to the degree of blast energy. Correct? Yeah? I think that's a sort of a time-related process. So you can have back fracturing into the pillar, and then slabbing of material is a function of time, the degree of slabbing. I think the only techniques that I've personally seen are what's called an ELOS, E-L-O-S, estimate for, it's an empirical method of estimating the degree of slabbing. So you have a design outline for a stope. This will predict, given the spans, say level interval spans, strike, stope width, will predict you might have, say, 1-2 metres of material that will come off your hanging wall. You might have, say, half a metre come off your foot wall. So you can use that sort of technique. Does that answer your question? Or not really?
Можно я задам вопрос? Большое спасибо за хорошую лекцию о потерях и разубоживании. И вообще, вы изложили методику, которая применяется при проектировании карьера в 70-х годах. То есть привязка к длине контакта, его характеру, изменчивости и размеру ковша экскаватора. Это нормальная инструкция, которой пользуются все горняки, начиная с 3-го курса института, это применяется. Вот. А сегодня, задал мой коллега вопрос, связан с тем, что, скорее всего, несовпадение планов и проектов и реальности по потерям и разубоживанию связано с тем, что муки и котлеты перемешиваются во взрыве, а не в горном массиве. Поэтому, когда происходит взрыв, горная масса перемещается на десятки метров, а мы пытаемся поймать селективно обработать 10 метров рублей, 3 метра рублей, или там наоборот, 3 метра прослойку брать. Поэтому современное состояние горной науки движется в том, чтобы учесть именно этот процесс. А те методики, да, на уровне предпроектных решений, наверное, да, они имеют место быть, они дают очень приближенные параметры потери разубоживания. А на практике, в реальности, наверное, есть новое направление. Вот хотелось бы услышать от вас, поскольку вы знаете практики применения в мире. Насколько учитывается этот фактор? Смещение именно при взрыве.
Yeah. Okay, from a practical perspective, during the 80s, certainly in Australia, in my experience, with an open pit, you would implement what we called blast vector indicators. And essentially what that is extra drill holes throughout a shot with a white plastic pipe inserted, no explosive, just inserted in the shot. That would be blasted, say, on a 5-metre bench. Following the shot, surveyor would pick it up, and that would be used. You'd have 2 or 3 of those in a shot. That would be used to provide an indication of movement along strike, the ore body. The direction of the blast was always orientated along the strike of the ore body. And the predominant movement of the shot is always, therefore always on the strike. With modern electronic detonator systems, you can control exactly what angle the blast moves at. The blast vector indicators also gave us an indication, more importantly, what the movement was across the strike. And that was the key one. And what our practice was to mark up the ore pattern before blasting. So you would see it might be marked in lime, it might be marked in a dye, it might be marked in flagging tape, coloured flagging tape. That would be marked up before the blast. Then after the blast...
I'm not getting it, I'm sorry.
Я прошу прощения, да, это понятно, что на сегодняшний момент геологическая модель является основой для любого моделирования горных работ. На сегодня я спросил не о том, что это важно или не важно, а о том, есть ли это в мире. На сегодня в России ведутся на нескольких рудниках большие опытно-промышленные работы по закладке реперов, по моделированию, реальному моделированию взрывания с учетом заряда, скоростей взрывных взрывчатки, с учетом денсити коммутаций, с радиоэлектронными методами мониторинга, различными технологиями, проверяющими реальные потери разубоживания в взорванной горной массе. Есть ли такая практика в мире? То есть если вот мы можем на стендах там показать, потом, если подойдете, уже реальные взрывы, проведенные на золоторудных месторождениях, на железорудных месторождениях. Вот. И выйти, все-таки уйти от этой практики ориентировочного расчета по длине контакта и ковшу экскаватора, выйти на реальные показатели, которые реально повысят экономику от работы. Есть ли такие практики?
Yes, definitely. I mean, there are companies that provide blast monitoring balls. There are certainly Australian companies, and there are companies in Europe that offer that as a service. It's not cheap. I think the balls are around $300 US each, and you may need to install between 3 and half a dozen in a shop. So it can be expensive. I can probably put you in touch with. We had a presentation from one of the directors of the company in the past 6 months. But they use these balls, and then they use computer algorithms to interpret the movement of the ore and waste in the shop. Just a word of caution though, one of the case studies that we talked about earlier actually implemented this and was using it. It can be quite difficult for a very hard rock environment where you have movements of 5 or 10 metres, preferably a long strike rather than a cross strike. Some of the other issues that you have is that you have a limited number of data points that you might be trying to relate to a large mass. So there's an inherent level of accuracy issue with that. The other issue you face with the blast movement monitors is that generally you have a failure rate of around about 10%. So the blasting balls that you put in the shot, you'll lose 10% of them. So, but there are some papers on projects that have demonstrated improvements of quite significant improvements. But you really do have to look at it, assess it critically to establish that the claims that they're making, some of the companies particularly that are selling these services, are valid claims. But certainly it's out there. Yeah.
Сейчас, конечно, я дослушал, извините. Речь идет не о датчиках, а речь идет о компьютерных технологиях моделирования взрыва с учетом заряда, сети коммутации. То есть современные математические, физико-математические технологии, модели развала горной массы с учетом баллистики, перемещения элементов, с учетом биологического строения. И вот это высоконаучные технологии. А то, о чем мы говорим, длина контакта и ковш экскаватора, это 70-е годы.
Oh, okay. Some people that do that sort of modelling, Queensland University of Technology, CSIRO in Australia, they have industry-funded investigation of those sort of modelling techniques. The only other thing I can suggest is it's one thing to have a model, you've got to be able to test the model. There are techniques for fragmentation analysis, post-analysis of shots, and that's a sort of investigation work. But certainly, I'm not personally familiar with those areas, but I know some of that work is being done. We could look into it further for you if you like. Time for one more?
Можно. Я себе говорю, можно. Во-первых, спасибо вам за доклад. Содержательный, доступный. Я хотел бы сделать одно замечание, которое не имеет отношения к вашему докладу. Перевод на русский язык был для нас, оскорбительный. Допустим, перевели open pit как открытая яма, или underground как подземный ход, или head grade перевели как головной мозг. Вообще это для телевизионной передачи юмористической. То есть они вас обидели, вас лично обидели таким переводом. И хотел бы вот что сказать. Вот мы у себя на производстве, на предприятии, где я работаю, мы сейчас занимаемся вплотную большими вопросами снижения разубоживания, в первую очередь. Разубоживание потери друг от друга в некотором смысле зависят, это вы знаете. И, допустим, мы добываем медную руду, жильную, кукопадающую, мощностью от 15 до 80 сантиметров. Содержание меди 3%, золота там 0,8 грамма, то есть очень богатая руда. Но когда добываешь, получается совсем другая руда. Уже мы не можем это сделать, вы не понимаете, что человек там не помещается, оборудование не помещается. Вот. Поэтому есть другие способы, о которых надо помнить и этим надо заниматься. Есть способы предварительного обогащения перед тем, как отправить на фабрику. Мы всегда этим занимаемся, у нас проект сейчас в работе находится. Я думаю, что в этом году мы 3 проекта на 3 рудниках запустим. Предварительное обогащение, вы знаете, бывает рентгенорадиометрическая сепарация, магнитно-сенсорная сепарация, фотометрическая сепарация. И этим можно, не отправляя на обогатительную фабрику, прямо подняв по стволу или даже под землей, провести сепарацию и получить гораздо более богатую руду. Допустим, мы получаем 40% руды, отбиваем после сепарации, содержание 0,11 меди остается, а 60% уже идет, на 40% мы сразу не отправляем на фабрику, остается в отвале, а 60% содержания 3,5% идет на фабрику. То есть это тоже вопрос оказания влияния на разубоживание потери. И надо будет, экономику когда считаешь, надо будет, наверное, учитывать и учет вести повышение или снижение извлечения на обогатительном периоде. То есть есть допустимый предел разубоживания, допустимый предел потерь, при которых вся экономика сквозная от добычи и кончая обогащение, получение концентранта, покажет, что такое, допустим, даже повышенное разубоживание может оказаться более эффективным, чем меры по снижению разубоживания. Вы понимаете, что в шахте добиться снижения разубоживания, особенно при узких залежах, это очень трудно. Спасибо.
I agree. Just one final comment on that. The post-processing is probably right at the cutting edge, things like ore sorting. For the underground, the hard rock gold mine that we looked at earlier, we investigated some techniques for ore sorting. There are some opportunities there. As an example, we reduced the cut-off grade from around about 0.6, 0.7 grams per tonne down to 0.3. And that's a function of the ore sort of mass yield and gold yield and the sort of distribution of material that you have to crush and process. But an interesting area of development. And with that, I'll conclude and hand over to my colleague. We're having a short break. Yeah, short break for coffee, and then Carl Llewellyn will proceed with a talk on geotechnical aspects. Thanks very much for your time.